Welcome to Grade 11 Artificial Intelligence. In this module, we study the most important idea in machine learning theory, the balance between bias and variance. It explains why a model can do well on the data it trained on and then fail on data it has never seen. Master this and you'll understand how to build models that truly generalize. Here is our plan for the lesson. We'll begin with the true goal of learning, which is to generalize. Then we'll define bias and variance and see how the error of a model breaks into three parts. We'll learn to read learning curves to spot underfitting and overfitting and meet two tools that control the balance: regularization and cross-validation. Finally, we'll state the no free lunch idea, which keeps us humble about any single method. Imagine training a model to predict maize yield for farms across Rwanda. We can only collect data from some farms, yet we want the model to work on farms it has never seen. That ability, performing well on new, unseen data, is called generalization, and it is the real goal of learning. To measure it honestly, we split our data into three parts: a training set the model learns from, a validation set we tune against, and a test set we touch only at the very end. A model that scores well on its training data has proved nothing yet. It might have simply memorized the answers. The test set is the honest judge of whether it has truly generalized. There are two distinct ways a model can be wrong, and these dartboards make them clear. Each shot is the model trained on a different sample of data. The bullseye is the truth. Bias is systematic error. A high bias model is too simple to capture the real pattern, so its shots land far from the center the same way every time. Variance is sensitivity to the particular training sample. A high variance model changes wildly when the data changes, so its shots scatter widely. The top left board is what we want: low bias and low variance tightly clustered on the truth. Most real models trade one against the other, and our job is to balance them. We can be precise about all of this. The expected error of a model on new data splits into exactly three pieces. The first is bias squared, the error from a model too simple to capture the true pattern. The second is variance, the error from the model being too sensitive to the particular sample it trained on. The third is noise, the irreducible randomness in the data itself, which no model can ever remove. Now watch the trade-off. A simpler model has more bias but less variance. A more complex model has less bias but more variance. Total error is smallest, not at either extreme, but at the balance point between them. Finding that balance is the central craft of machine learning. How do we tell in practice whether bias or variance is the problem? We plot a learning curve. On the horizontal axis is the amount of training data. On the vertical axis is the error. The blue curve is the error on the training set, and the red curve is the error on validation data. If both curves sit high and close together, the model is underfitting, that is high bias. If the training error is low but a large gap remains above it, the model is overfitting. That gap is the variance. Notice that adding more data shrinks the gap, which helps a high variance model but not a high bias one. The curves tell you which problem you actually have, so you fix the right thing. Two tools let us control the balance directly. The first is regularization. During training, we add a penalty for complexity, which pulls the model towards simpler solutions. This lowers variance, sometimes at the cost of a little bias, and the strength of the penalty is a knob we tune. But how do we tune it fairly without peaking at the test set? That is what cross-validation is for. In k-fold cross-validation, we split the training data into k equal folds. We train on all but one fold and validate on the fold we held out, then rotate so every fold gets a turn and average the scores. This gives a reliable estimate of how a setting will generalize, so we choose by skill, not by luck. It would be wonderful if one algorithm were simply the best everywhere. The no free lunch idea says this is impossible. Averaged over every possible problem, all learning methods perform the same. A method that wins on one task can lose on another, so there is no universal champion. Good results come from matching the method to the structure of your particular problem. The assumptions a model makes, called its inductive bias, are exactly what let it learn at all. The practical lesson is humble but powerful. Never trust hype about one best model. Always test candidates on your own data and let the evidence decide. These ideas decide whether real systems can be trusted. In Rwanda, a crop yield model trained on a few districts must still work on farms it never saw, or it is useless to a planner. In the United Kingdom, a hospital risk score is judged on new patients, never on the patients it was built from. In the United States, a spam filter that overfits memorizes yesterday's spam and misses tomorrow's. And a mobile money fraud model must be retuned as fraudsters change their tactics because the world does not stand still. In every case, the rule is the same. Report how the model does on unseen data, never on the data it learned from. Before we recap, let's clear up the common misconceptions. First, a low training error does not mean a good model. It may simply be memorizing. Second, more complexity is not always better because every added degree of freedom raises variance. Third, collecting more data helps a high variance model, but it will not cure high bias from a model that is too simple. Fourth, never tune your settings or choose your model using the test set. That quietly leaks the answers. And finally, remember that noise is irreducible, so no model can ever push the error all the way to zero. Hold these in mind and your judgments will stay sound. Let's gather the key ideas. The goal of learning is generalization, performing well on data the model has never seen. Bias is systematic error from a model too simple, and variance is sensitivity to the particular sample. Total error breaks into bias squared, variance, and irreducible noise. Learning curves let us diagnose underfitting against overfitting. Regularization lowers variance, and cross-validation lets us tune fairly without touching the test set. And the no free lunch idea reminds us to match the method to the problem. Now, let's check these ideas with 3 quick questions. Here is the first question. A model scores 99% on its training data, but only 60% on the test set. What is happening? The training error is tiny, but the test error is large. That big gap is the signature of overfitting, which is high variance. The model has memorized its training data instead of learning the general pattern. Question 2. Your model is underfitting with high bias. Will simply collecting much more data fix it? No. More data shrinks the gap caused by variance, but it cannot rescue a model that is too simple to capture the pattern. To cure high bias, you need a more capable model or better features for it to learn from. Last question, and it ties the module together. Why must we tune the regularization strength using cross-validation and not the test set? Because if we choose our settings by looking at the test set, we are quietly fitting to it. The test score then looks better than the truth and no longer estimates real generalization. Cross-validation lets us tune fairly, keeping the test set as an honest final judge. Excellent work. You now understand that the real goal is generalization, and that error splits into bias, variance, and noise. You can read a learning curve, diagnose underfitting and overfitting, and use regularization and cross-validation to find the balance. In the next module, we'll move to advanced language understanding with transformers and BERT. I'll see you there.